We're recording. So, today, uh, we're talking about chapter 2 of. God damn it, what's the. Man, the title of this book is huge. Concepts, Techniques, and Models of Computer Programming. Thank you. Okay, so chapter 2 is about declarative computation model. So let's ask, what does it mean to be declarative? I think that's the main question. Like, I read halfway through, and only then I was like, wait, do I know the answer to this question? I don't know if I know.
Okay, first point, you are not sharing the screen on Discord yet.
Yep.
Not sure if you're supposed to be.
All right.
Secondly, what is declarative? What is declarative? That's a deep question, Lemos.
Well, it shouldn't be because the book the title of the chapter is declarative computation model, but it's very hard for me to grasp exactly why are you using this terminology? What does it mean to be declarative in this author's minds? And as far as I can
uh,
tell, my best bet is about the store. Actually, that's
is about the store.
yeah, that's as far as I could go to try to find a definition for declarative. It's about which type of store are we using because it goes lengths to say about the value store and mutable
Um,
stores and
I think it's
single
a
assignment
little.
stores.
I think it might be a little bit. Well, the stores are definitely related to it, but it might be a little bit deeper because we have the. We're going to get into the declarative concurrency model later. Um, and it's still declarative, even though it's concurrent. And the key point there is about whether or not, if you run the same program twice with the same input, you get the same answer.
Is that a definition of declarative? Why is not why are we not calling this the deterministic computation model?
Because hmm, it's a good question.
Yeah, so
Technically,
go on.
technically, the declarative concurrency is non-deterministic in execution, but not in semantics.
Doesn't matter. Like in that particular case, you can pick and choose what are we pointing to be deterministic or not.
Well, I suppose you could call it the. I suppose you could call it deterministic. If you want to mean, okay, it's declarative because it's deterministic. Same input, same output. It's repeatable. Um,
Well,
does
if
not.
you're if you're gonna go through that definition, why not call this the referentially transparent computation model? Like we can
That's
go
kind of.
we can go here on and on and on. Like I'm having a problem with like what is the semantics of
Um,
this term?
is this really, really referentially transparent when it has single assignment variables, though?
Well, I mean, you said it yourself. It's the same input, same output. I'm not even like I'm not being pedantic. I'm not trying to be pedantic. I'm just saying that if you try to be pedantic, you're gonna have a problem. Well, at least I had problem with this, whatever this means. And Willie said something. So Bob Harper's article on declarative programming, the declarative nihilist, if you will. Well, I haven't
Hmm.
read that one, but I
Well,
definitely have
something.
doubts about what is the meaning of this term.
Well, it's something to look at later. At any rate. Well, we will see this throughout the chapter, but basically this model is like, yeah, it's purely functional programming with logic variables
Yeah,
essentially.
yeah. So this is sometimes called stateless programming.
Yeah, because there's no explicit state, right? You don't have anything that's mutable, that's detectable in the language.
That's why I thought the store is the real deal. That's why, because it starts by saying, well, actually, we're not gonna read everything because it's 70 pages. We're gonna try to skim through it. So first, a computation model, which is a formal system that defines the language and how sentences of the language are executed by an abstract machine. That's a computation model. A set of programming techniques and design principles used to write programs in the language of computation model. We call this programming model. Um, and then third, a set of reasoning techniques to let you reason about programs. So we have something related to an abstract machine something related to best practices and techniques, and something that is related to reasoning. So that seems fair. And then we have a summary of the chapter, and then we start getting into the kernel language. So the first thing, and which well the basics, right? So grammar, not surprisingly. So then we have the simple. Well, I wouldn't. Well, maybe definition is not the right word, but these these things. So we have statement being also called a sentence, which is a sequence of tokens. And we have a token or word being a sequence of characters. And then, well, this is essentially what we write, right? We write these things, and then it gets processed by something else, by another program. And the one of the first steps usually of these other programs is to check the grammar of things. And then we go to extended Backus-Naur form, very classic. So this is how you can define a grammar, and then it goes lengths to explain the difference between context-free grammar and contextual grammar,
Yeah,
context-sensitive grammar.
pretty basic stuff at the beginning of this chapter. It's a very good introduction actually for someone who never looked at parsing
Yeah, but I
before.
wonder I wonder why this is in here in a particular sense. Because in the beginning, he says that no, you should not use this book as your first reference for learning programming. But then these things
Well,
comes along.
well, this is not really assuming that you don't know programming. It's just assuming that okay, maybe you know programming, but you never dealt with parsers before. So let's get into grammar.
No, but that's exactly my point. Like this is a pretty good introduction for somebody that is trying to understand what the fuck happens when I do GCC whatever.
Well,
Clemens,
well,
Go for it.
go on, Nathan.
that's that's a really good point. But in practice, people do completely the other way around. As in, you learn how to program in Intro to Programming, and one of the last courses on Uni, it is like compilers and shit, and only then you take a look on what actually happens.
Yeah, but it doesn't like I understand what you're saying, especially because I was there. Like I did 5 years of computer engineering. It exactly the way that you said. We first learn programming. Well, the act of writing programs, and then we learn about compilers and interpreters. But in retrospect, the reason that I did do these questions is because the courses were ass, right? Like, it make more sense when you start to learn, I don't know, a natural language? You always start by the grammar, right? Like, what are the verbs? What are the structures of the sentences? That's when you start learning things for new natural languages. Why are we not following the same practice for programming languages?
That's a very good question. Also, to be fair, the book says it's not meant for complete beginners, but it does say, okay, you could make a course for beginners to programmers with some modifications, right? That's a point that we didn't touch on last time, but
Probably because of the distinction between linguistic abstraction and string triggers. Yeah, yeah. No, we're gonna go through that, Uli, but like I find it again in hindsight. If I did have the time to care about those things, because when I did my first programming course at uni, it was pretty rushed. If I was instructed more properly and I had more time, of course I like makes way more sense to okay, I'm typing shit. What does this even mean?
and how do we know what it means, right?
And I'm not even saying, for example, that oh, I must now know and write by myself a context-free grammar. No, 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 no. Maybe that should be an exercise in the compiler's course. But to know about it, to know that its existence, that sounds pretty reasonable to me. Um, anyway, so I think everybody here is pretty accustomed to EB and F, right? So I don't think it's worth going through that in detail. And then it talks about precedence, which that's valid. Syntax notation used in this book. More details about syntax, and then have a little bit more refined syntax. Language semantics, right? So this again, pretty much. like in natural languages, there's syntax and semantics. So syntax is about, is this construct acceptable? Are we gonna can we at least check that it's following some rules? And then the semantics is what this thing actually means. And this is not that different. So we're gonna try to understand what this means. So, oh yeah, and then it goes from the translation portion, right? So we have the code that you write, and then that gets translated to a more kernel language that has fewer built-ins, which is pretty much in this case works like an intermediate representation. And the choices of what's going to be the primitives slash built-ins are pretty important in this particular case because it pretty much goes against all intuition that at least I had about, okay, what's going to be my built-ins. I would say um, let's start
Functions.
with not functions. I would start with literals, like we're doing with Karuta. To me, what we're doing with Karuta is pretty natural. Okay, we have some
I
stuff to
mean, if
organize it, but we don't have a way to express what's inside of them. So let's do literals now.
I
This
mean, if you think,
just says fuck it, let's do procedures.
I mean, if you think about the lambda calculus just has abstractions, basically, right? Lambda functions. Like it doesn't have, unless you extend it with literals for other data types, it
Yeah,
doesn't have them by
but
default.
this is based on operational semantics, right? Lambda calculus is exactly what this thing is trying not to do, and it's pretty explicit about it. It wants to go through the route of operational semantics on purpose. Like anyway,
That's fair. That's fair, but also operational semantics. What's the operational semantics of a number? There are none because it's done. It's a number. It's not code, right? It's just
so
plain data.
I guess the answer depends how the numbers are encoded. Because if they are piano numbers encoding, then the numbers actually do have more semantics than just their own existence.
Well, they have a structure, but they don't have like they're not code that you can execute, right?
Well, of
They don't
course.
perform operations. They are arguments to
Yeah, no,
operations.
no, but they mean something. They mean how many times you went over the zero, right? Their encoding kind of tries to portray that meaning. With just a true is just a true, like whatever. Well,
Mm,
anyway,
I,
this is what Willie was talking about. So define transition scheme for full programming language to the kernel language. And then we're going to go through linguistic abstraction, which is essentially extensions to the language. But extensions that actually are powerful in the sense they're not just an easier slash more convenient way to write something else, which in this case is going to be syntax sugar. Um, and
well, a
then we go,
linguistic abstraction for well, if you have intuition from Lisp, a linguistic abstraction is basically a macro, essentially, right?
yeah,
You have a form in the language that's more express, it's more concise, more convenient for you to use, and it gets translated into a simpler form that's more convenient for the machine later.
yeah. Uh, and then we have a contrast of all of four types of semantics. And I had a question about this. I just don't remember. Oh yeah, I think that my question was about what is the difference between axiomatic semantics and logical semantics?
What's the
Because
difference between
yeah,
them?
it's specifically saying that an axiomatic semantics defines statement semantics as a relation between the input state and the output state. Gives a logical assertion. Like, isn't this prologue logical assertions?
Not quite, because when you're programming in Prolog, um, you don't do assertions during the course of evaluating a predicate. You do those before you actually run the program.
I don't follow. I thought when you execute like triangular numbers in prologue, you are actually trying to find the assertions that are true.
You are trying to, by implication, check whether a predicate holds or not. And if you have three variables, you're trying to find the bindings that make the predicate hold, right?
Yeah. How is that not a logical assertion?
You're not really you're not really asserting anything new, is the point.
New. Okay, that's different. Okay, so why does it have to be new?
Uh, like you basically, when you execute pure prologue, right? If you forget about side effects for a moment, you're basically just doing deduction, right? Um, you're not really saying this must be true. You are saying, okay, I have a predicate. Does this hold or not?
I'm having trouble, man. Isn't it the fact that when you say for with these variables with these values, this is true? Isn't that a logical assertion? I'm confused.
Yeah.
Uli is saying something about separation logic and calculi. I have no idea. Like I was pretty confused about this because like this makes sense. Abstract machine. This makes sense. We're talking about those functions over an abstract domain. But then these two, I'm kind of like, okay, but you're gonna have to talk a little bit more than that because
Like axiomatic semantics is more like, okay, you have this impure thing, like you have explicit state in your language or something like that. And you have to give a semantics for that, but you can't really rely on just the semantics that you would get by interpreting the your program as a set of predicates, right? Because that doesn't really work if you have mutable stuff. Instead, you have to do something like, okay, if you do this and the state before is X, the state after is Y.
oh, so this is just like a Turing machine type of thing.
It's like you can use it for Turing machines, I suppose.
Yeah, this is reminding me of Tula.
Yeah, it's kind of like OR logic, pre and post conditions essentially, right? You say, okay, given this precondition, you can run this, and then this post condition will hold afterwards.
Oh man. Okay, this language got way more well, actually not really. Okay, wait, it's 59 lines for a universal Turing machine. Okay. Yeah, no, but it's exactly what you said, right? So you say what is the state before. What is the? Let me see an example here. Yeah, you say what is the state before, and you tell it which state is next.
Yeah,
Okay. Yeah. Okay. I see.
yeah, we're gonna see
Process
some
linguistic
examples of
expressions
that.
as logical formulae. Okay.
Yeah, as the book mentions, we're gonna see some examples of that on chapter 6 when we get to mutable state.
I need to go a little bit faster because it's already 20 minutes. Okay, so linguistic abstraction. So yeah, so I think this is pretty important to distinguish between syntax sugar and this thing. So I remember the linguistic abstraction goes through phases, right? So I don't remember where it talks about that, but anyway. Oh, okay. Yeah, phases. So you two phases to defining a linguistic abstraction. We define it as a grammatical construct, and second, define its translation to the kernel language. So how are we going to write it, and then what's actually happening with it? So the example that is doing here is about the for construct to do certain kinds of loops, and it calls that declarative programs. The new construct is both an abstraction in addition to the language syntax. Yeah, so this includes new syntax and it can be translated to. Yeah, but the main important part, so def macro and macro expansion. Yeah, but here's the thing. Now in retrospect, this definition is actually a little less nice because when you're creating syntax sugar, that also requires a grammatical construct, right? You need to allow that syntax to be valid. And you also need to tell it what it actually is under the hood. So these two phases are kind of like doesn't help.
That is fair, but also I guess the difference that he's trying to make here is that syntactic sugar tends to have a relatively trivial translation, whereas with um, with linguistic abstraction, that's not necessarily the case, right?
Wait, repeat the distinction there.
Like when you have a linguistic abstraction, the translation to the kernel language may not be trivial, right? With syntactic sugar, it tends to be because
That's
you're
not
not really
written here.
introducing.
You are trying to see a pattern in the examples given, and I appreciate that. But would you agree
But,
that that's definitely not written in here?
but there's a reason for that, and the reason is actually written there. It's because with syntactic sugar, you're not actually introducing a new concept, you're just extending an existing one.
But that's the thing. In the linguistic abstraction, it doesn't actually say that you're introducing a new concept. It says that you are introducing a grammatical construct and a translation to the kernel language. So if you're going to talk about new constructs, you need to define what the fuck what do we mean by that. Because given these rules, both of them are doing the same.
Well,
And I am being pedantic, but well, I'm reading Richard fucking Mitchell, okay? So give me a break.
that's fair, but also, coming from a Lisp background, I don't really see much of a point of making this distinction, to be honest.
That's fair. That's fair. Yeah, so Uli is saying that my analogy is a syntax tree is like a C macro, in linguistic abstraction is like a Lisp macro. Yeah. So essentially, you guys have the intuition of being more powerful, being more. You can do more stuff with it. Not what the heck is going on in here. Like it really doesn't go that into that rabbit hole of like expressiveness and power. But anyway, I think this is well. That's okay. Uh, yeah. So, but it should not be confused with linguistic abstraction. It does not provide a new abstraction, but just reduces program size, improves program readability. But are you defining a new abstraction? What is the meaning of saying that then? Because you just said that it's a matter of grammatical construct and kernel language. Is that a new abstraction? And if that's so, why is the syntax sugar not one? Maybe, and just to wrap this up, maybe it's because when you, even though these things are linguistic abstractions, you think of them as separate entities.
Mm,
Like, even if I told you that fun is a linguistic abstraction, we tend to do a maybe artificial separation between the fun and the proc. Even if I told you they one ends up like the other. And then with the syntax sugar, it's actually more helpful and more prudent to think of it as a translation. Maybe that's the difference.
um,
I don't know. Hard to say. Uh, okay, so language design. Well, you want to say something, Mari?
I was just gonna say, the intuition I have is like, okay, if you can add variables and you can declare variables to be numbers, and then you say, okay, this is inconvenient as heck. Let's just say you can add numbers together and we translate that to just we declare the variables anonymously and then do the addition on the variables. That's kind of what it's going for a syntactic sugar in the sense that yeah, you could do this the long-winded way, but it's just shorter to do it like this, and we don't really lose any of the meaning, right?
But that's the thing. When you're writing a fun instead of writing a proc, you could do the proc instead, but the fun is just more convenient because it takes less characters. And that's the thing. I think it portrays more when we think what we are trying to think. That's why this separation may matter. But from what you said, I don't know, maybe writing a proc is just as easy as writing a fun sometimes.
Maybe. Willie
Um,
says you have to disappear and reappear in a minute,
yeah,
okay?
see you in a bit, Tuli. So any abstraction that we define has three phases in its life cycle. We first define it and it has no linguistic support. So this is actually we're thinking if we should. Okay? Okay, so we are discussing and that and then Marinho proposes, okay, let's add integer predicates to Karuta. Doesn't exist yet. It's just we define it. So what's this thing's gonna do? What is its purpose? Why should we need it? So there is no syntax for it, and um, and then at some point we suspect maybe that is especially basically useful and you can decide to give it linguistic support. So then we go to the lecture and the parser and say, okay, now you guys recognize what the fuck is this. That
Yeah.
seems that's fine. And then it becomes a linguistic abstraction. This is an exploratory phase. There is no commitment that the linguistic abstraction will become part of the language. This is a little weird, right? Because in order for you to test it, it needs to be part of a version of the language, right?
Uh, try to think of it like this. Here he's trying to make a distinction between, okay, we defined a macro, you can use it, it's fine. And then later we can say, yeah, no, this is so useful. Let's actually make it a built-in of the compiler instead of a macro. But we know it came from a macro originally because then the compiler can do some extra stuff, you know?
That's not written here.
Well, it is. It says if the linguistic abstraction is successful, then it becomes part of the language. That's how I interpret that, at least.
No, yeah, I can understand that, but the way it said it, it seems to me that we first think about it, then we add syntactic support for it, and then we see how it holds. We see if it's bad. We see if people make very bad stuff with it, and if it's good, we just let it fly to when in the next release. What
That's
you're
fair.
saying is that okay, after we see that it's actually useful and not harmful, we go back. We actually we go back on our steps, and then now we make it maybe properly, whatever that means. But
Not
that's
really properly, but more integrated, I guess.
yeah. But when I said properly, it's because you may have something that works, but is not ideal because it may have more trade-offs than it needs. It may give the wrong intuition. When I say properly, I mean like okay, let's make it built-in, or let's actually cut some corners. Let's actually change its internal implementation because it's too slow. Whatever properly means.
Okay.
Okay, other translation approaches. The kernel okay, so then we have the foundation approach for the mathematicians, such as Turing machine, lambda calculus for the first order logic, and we also have the machine approach that intended for the implementer, programs that translate to an idealized machine, which is traditionally called an abstract machine, or VM. This is what we did for Karuta, right? Because I was kind of
We
confused. Are we using kernel language or VM in Karuta?
in Karuta, that's actually a VM because it has a notion of it has an actual explicit notion of memory addresses, which is not really something you need for a kernel language.
That's fair. Okay, so the kernel language is still high level in a sense.
Yeah, it's still high level.
This is not that high level. And then the interpreter approach, which is actually kind of funny if you think about it, because who who and how are we grabbing the three primitives and doing stuff with it? Doesn't he have an interpreter? What are we talking here?
Well, the approaches before were about, okay, I have a program, I'm going to translate it into a different form that I can then execute, right?
Yeah, no, but I think it's misleading to say that it's an alternative in the sense that we are not doing that. But because I kind of have a little bit more experience than a noob in programming, I must assume that they do have an interpreter.
Well, you need to have an interpreter at some level. The question is, do you define a kernel language and interpret that, and then the rest of your language is translated to that, to the kernel language? Or do you just define the language directly in the interpreter? Don't bother with the kernel language at all, because that's the approach that a lot of scheme books take, actually.
No, but that's the thing, right? So even if they go with the kernel language, they have two options, right? They either compile it to whatever architecture they're running this thing, or they have a separate program that interprets the kernel language, right?
You, well, yes, and you could do both together, actually.
Fine,
Um,
but given no context, I don't know us. I assume that okay, these guys probably have an interpreter that is grabbing the kernel language and doing stuff with it. Am I crazy?
mm,
Do they compile this to x86?
I'm not sure, actually. That's a good question. I should check that at some point.
Well, someone could even argue that compilation is actually interpretation in which the hardware is the interpreter, but anyway.
Actually, more people would try to argue that compilation is really just interpretation with partial evaluation. You're partially evaluating the interpreter to specialize it to this particular program. And that's basically what you do in a compiler.
Wait, I didn't get the final part. I didn't get the partial evaluation thing.
Like, when you have a function and you partially apply it to some arguments, and you're expecting more arguments to come later, right? You actually have an opportunity there to to optimize the function for the arguments that you already have, right?
Sure.
In that sense, you can think of it as okay, a compiler is really just I have an interpreter, I partially apply it to a program, and then I optimized it, and that's a compiler.
Well, the rest of the input is would be the input to the program.
Yeah,
That makes sense. I never thought about like that. Every time, well, the only funny interpretation I had was okay. What if the hardware is the interpreter? Then
that's
everything is
also
an
a way.
interpreter.
Yeah, no, that's also a way to look at it, and both ways are useful, but for different purposes.
Yeah, but these are they actually have some arguments in here. We do not use interpreter approach in this book because it does not in general preserve the execution time complexity of programs. That's very fair. A second difficulty is that basic concepts interact with each other in the interpreter, which makes them harder to understand. Just don't show the interpreter, man. Like, I don't know what. Okay, then we go to man. This is gonna take a while. We are halfway there, halfway in the time, and not halfway in here. Okay, now we go to the store thing. So again, it took me a while to notice, but there is a difference between these axes and the capital axis. In fact, they are different.
They are.
So these axes are the axes that are probably random and created within the store.
Yeah, they are the actual physical variables that are stored in your computation model in the memory.
But yeah, that's a very good question. Why would you do your VM like that at all?
Because the label that identifies a variable and the variable itself are two separate things.
No, they are separate things. But either one of two things. Either this is like we're gonna go in the future about like we're gonna go and develop the when reading the book about conflicts of variable names, and we're gonna and then this shit's gonna be useful as fuck, or this is just a choice that they decided to put it now instead of later.
Well, this is useful because it gives you a natural way to model shadowing as opposed to binding a variable. Those are two separate actions, right?
Okay, that's fair. Okay, so essentially the single assignment store. So when you create a variable, you become and it's uninitialized. We're gonna see syntax sugar for initializing it later. Um, but it starts as an unbound, and then you can do, for example, equals to bind them, right? And again,
Yep.
these axes are not the same axes that you write in your program. That's very important to notice there. And then we have declarative variables, which are also called data flow variables because they have that property that we talked about last time about being able to wait and be
Yep.
smart. And then we have comparisons with other stores. We have the value store. And the reason that this is different, because in the first moment you may say, okay, but how the fuck this is different than whatever single assignment store is? The difference is that this is always locked to values, and this is not necessarily so, as we will see later. Um, so all of these examples are value mappings, right? So bound to values.
Yep.
Functional languages like SML, Haskell, Scheme get by with value store since they compute functions on values. Um, and then you
Yeah,
also
it
have
does.
the cell store, which is the mutable
Yeah.
one.
Yeah.
Uh, and also because single assignment stores allow us to use partial values. And partial values is also criticism. I would like to have partial values column and then text. That doesn't happen. But partial values is essentially when you have something in your value, such as for example this list, that is yet to be known. So if you have instead of a 3, you have a y that doesn't is not bound to anything yet, That's classified as a partial value.
Yeah, because you have a variable, you don't know what value that variable is supposed to hold, but you know it's there, right?
Hmm. So this allows us for partial values. A procedure can return an output by binding an unbound variable argument. And the second reason is because of declarative concurrency, which we're gonna see later. And the third reason is that it's essential when we extend the model to deal with relational programming and constraint programming. Other reasons have to do with efficiency, such as table recursion, different lists, of course. And then now we have value creation, which is essentially like it looks like we're doing an assignment, right? So
Yep.
we do this, and a value refers to a value. So this is in the value identifier referred to in an unbound value. So this is the x that you write, and this is the x. This is the internal, like I said, probably random created thing.
Yeah, it's the internal representation of the variable that you declared.
And then a variable identifier referring to a bound value. So this arrows to that, and this is a list. And now we have variable identifiers, which essentially like does this arrow here.
Yep.
Um, and then this is where we get into the mess of talking about environments because we're gonna put closures on this thing, of course. Um,
I mean, why wouldn't you, right?
well, I don't know Osman. What should I assume actually? I don't know.
Well,
Rust
it's a
doesn't have
reasonable.
closures. Jai doesn't have closures.
But that's because closures require you to do an allocation. And Oz is not really particularly concerned about being explicit during allocations.
Yeah. The mapping from variable identifiers to stored entities is called an environment. So that's important to remember. And then as we see, variable identifiers in the corresponding stored entities are added to the environment by the local and declare statements. So here we have more examples, and this is a partial value, right? So it's not in the text, but it's in here. Well, maybe it is in the text and I just missed it. It's also possible, but that doesn't matter right now. This is a
Oh,
partial
there
value
is.
because this is unbound. That's
Oh,
right.
there is a section. There is a subchapter called partial values, I suppose.
Oh, so I just missed it because I was reading like, but again, this was 70 pages already in the thing, and I was like, okay, what is a partial value again? Oh, it's when it's unbound. But it was so far away that I actually forgot about it. That's fine. Following the links of bound variables to get the values called dereferencing. So yeah, so that a lot of these arrows have actually like they borrow terminology and a tiny bit of semantics from pointers. They don't work like pointers because they have the data flow trick, but they do have like dereferencing terminology here.
Well, yes, because normally when you're going to do an actual operation, usually you want at least the top level of your thing to be a value. So if it's a variable, you need to dereference it to get to the value, right?
Yeah, no, that makes complete sense. And now we can also define a complete value, which is a value that doesn't have doesn't have unbound things. And then we have more examples here. And then, yeah, this is what I meant. These things can actually be bound together. And what this means, right, is that well, not necessarily this case, but you can have like a cycle, and then you will define one, everything else like surrounding that assignment changes at a glimpse.
Yeah, it's like when you have two separate variables and you say one equals the other, but neither of them
Yeah,
is bound.
yeah,
It does
variable and
that.
variable binding. So that's what this does. And then when you do equals to one, those should be equal. Both of them point to the list, right?
Yeah, you bind both of them when you bind one of them.
And then in the declarative model, we create a variable and bind it at different times. What happens if you try to use the variable before it is bound, right? So you that is unbound and you're trying to use it. We call this a variable user. And then we have some approaches to how to deal with it. Execution continues and no error message is given. That's terrible. Right? There's no
And
way
it's what
around
C++
that.
does.
Aside from you wanting to use the garbage because I don't know, maybe you don't want to use a random number generator or whatever.
That's a
Uh,
terrible way to get a random number, though.
well, but I'm trying to see excuses in which this would fly. Execution continues and no error message is given. The variable is initialized with the default value. So you can actually do that in C. So when you have a struct, um, you can actually zero initialize, so all pointers go to null, all inters go to zero, and then probably floats also go to zero, and blah 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 blah
But
blah.
that's something you kind of do explicitly, right? It's not done automatically, I don't think.
Yeah, you have to put zero in curly braces, I believe. Execution stops with an error message, so like you're gonna be notified, but you're not gonna do any. We're gonna stop, or we wait. Um, and then it
The
does a comparison
cases,
between that.
yeah, the cases are listed in increasing order of niceness. I love that phrase.
Um, I'm skeptical. I'm skeptical that this is the best way to do it, but I confess I never did data flow programming before. Not
Well, the second paragraph after this list does explain that. 3 and 4 are both reasonable, but in different situations, right?
well.
If you're doing a
It also
sequential
says
program,
that for it can be tracked by the debugger, but now I have to use a debugger because I don't know if I'm looping forever because of that or because of that.
no, but you're not gonna loop forever on case 4. You're just gonna block and wait.
Well, but that's
It's not
gonna look
really a
like
loop.
what?
It's gonna look like the program is frozen, basically. But
Which looks like similar to what?
well, it depends.
Like
Hmm.
we can distinguish these bottoms here. They are all bottoms. So am I
Well,
blocked here
at the
because
computer level, you could be like busy waiting or not.
no, of course. If I am observing the program, which is why it's suggesting a debugger, I can try to figure it out that actually I'm not looping forever. I'm actually waiting. But
Oh, that's
from
fair. No, that's fair. That's very fair.
so yeah, but again, I don't have any experience with this type of programming of like you're not gonna use locks or semaphores. You're just gonna do your shit, and it's gonna work. Fine. But about this order of niceness, well, I have to play with it to believe it. Okay, and then that's apparently the meaning of the data flow terminology that we're using here, which is fine.
Yeah,
Uh,
the book does mention that 3 and 4 are reasonable in different situations, right? 3 is for sequential programs where, yeah, if this thing is unbound now, it's going to be unbound forever because this is sequential. So it's better to just throw an error. Um, but 4 is like, well, no, this is a concurrent setting, so it's actually better to wait because maybe some other thread will bind it, right?
yeah. Okay, enough about stores. Now we go directly to the kernel language, and we start by talking about its syntax, and then we have a grammar here, statement syntax, value syntax, variable identifier syntax. I don't think any of these is actually that important. Actually, I do want to emphasize or to highlight this definition of a type. A type is a set of values together with a set of operators on those
Ah,
values.
that's not quite the definition I would go for, but whatever.
A value is of a type if it is in the type set. So it it talks about values being together in a set, but it also they come with a bonus, which is a set of operations on those values. Well, last time I checked set theory, that was not there.
Well, this is not really a book for mathematicians, right? It's a book for programmers. And if you don't have operations, then, well, statically I can check if some thread has the possibility of eventually binding the variable. That's not what Nathan wrote. The problem, Nathan, is that in general, to figure that out, you have to solve the halting problem.
No, 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 no. I'm not saying if it will bound, but if it can bound, as in it is being used on that thread, right?
That's
Then on
basically
at
garbage collection,
runtime,
yes. That's
then at
basically
runtime you can check if one of the alive threads. Yeah, yeah, it will only be complicated if a thread is waking up another and such, but I think you can still check, right? If
but
a
then
thread is
but then
alive, I
the
know if
problem
it can possibly bound or not.
the problem is that now the semantics of variable access depend on whether the variable is shared or not. Do we really want that?
Damn. Well, but I also agree with Nathan that with Marinho that what Nathan described sounds like well, it's very similar to what he's going to describe about garbage collection later anyway. Okay, anyway, so we have basic types that they are well defined set of types. Programs calculate with integers and records, which are all of integer type or record type. An attempt to use an operation with values of the wrong type is detected by the system in a rising error condition. Because of all uses of types are checked, it's not possible for a program to behave outside of the model, to crash because of undefined operations or behavior on its internal data structures. Yep. Yeah, but that's different than, for example, dividing by zero, right? So we still
Yeah.
need errors anyway. And then he calls, of course, and then he picks a side. You see, this is picking a side, right? So he could have chosen algebraic, but he chose abstract. So anyway, so this ADT is very particular.
There's a reason for this though,
We're gonna see in chapter
which we
three. I will be waiting
we're
for
gonna
it.
we're gonna see it not in chapter 3. I think it's, I don't remember actually when it introduces the concept of encapsulation as
It's
a
written here.
programming technique.
Ah, that I don't know. Basic types are numbers, records, and procedures. Again, very bold choice. So numbers, records, and procedures. Well, yeah. Uh, then we have dynamic typing, which is talking about. Um, yeah, so this is essentially like the definition of dynamic typing. We check some stuff at runtime.
Yep.
And then we have type hierarchy, which reminded me a little bit of subtyping, I think, in a
It
way.
is subtyping actually.
Okay. All tuples are records and all lists are tuples. We're gonna extend this hierarchy later. Then we go about more examples of the basic types.
We don't
Nothing,
need to take a look
yeah,
very
nothing too
deeply at those,
interesting in
right?
that. And
We
why
already know the
procedures,
types.
right? So the reason is because we're gonna have multiple outputs, which is cool.
Yeah, that's not something very common, unfortunately.
Yeah, yeah. You can do it in Racket, right?
Pretty much most Lisps allow you to return more than one value if you want.
Uh, a
Like you have
procedure can have
values
any
in
number of
Scheme, you
inputs
have,
and outputs.
yeah, you have values in Scheme and Racket. You have, I'm not sure if it's called values in Common Lisp, but you definitely have multiple returns in Common Lisp. You can do it in Lua, incidentally, which makes it 100 times better than Python just because of that.
Of course. Uh, okay, and then we have examples of basic operations, comparisons, procedural operations. We can actually check. Well, this is a dynamic language, so I'm not shocked. You can check if something is a
Yep.
procedure. And then you go to the semantics, right? So during normal execution, systems are executed one by one in textual order. Uh, and this book does something really great, which is to grab a program and do a step-by-step execution, explaining to you why, like, okay, from this state to the next state, this changed. Why? That's very good. I appreciated that. We talk about static scoping, right? And then we're gonna also talk, of course, talk about dynamic scoping.
Yep.
Um, okay, so there is a place here where he talks of where it's very. Let's read static scoping first. We can find out the scope of an identifier by simply inspecting the text of the program. We do not have to do anything complicated like execute or analyze the program. So that's lexical scoping.
Also known as static scoping because it's not dynamic.
Well, yeah. And then we have how to read procedures. So this is the name, this is the two inputs, and this is the output. The question mark is essentially like
It's a comment saying, yeah, I expect to treat it as an output,
yeah.
so I'm marking it as
And
such.
most and I actually doesn't mention. Do we have any call by values in OS, or is everything call by
N-
reference like Python?
no, Oz, everything is call by reference, but call by reference in Oz is not quite the same as call by reference in Python because, like in Python, the references are really just normal pointers. Uh, I suppose Python technically is call by reference, isn't it?
Yeah, it is. Like I know
There's a
very few
section
things
about
about Python, but
that actually. Call by reference versus call by value and other calling conventions way later in the book when we get to mutability because it becomes important there.
oh, of course. We have three identifiers, right? So you didn't declare the x and the y. So, well, spoiler alert, in the case of procs, these things are classified as like unbound, but they are actually saved because they are described in here. So that's
Yeah,
why
they are
this works.
arguments. Yeah, they are arguments, so they are not. They are free if you just look at the body by itself, but they are actually bound if you
Yeah,
look
yeah,
at the
but it does
procedure as a
does
whole.
that. And in the beginning it pissed me off because it says they are free, and I was like, wait, how does the function work then? And then it treats like this thing as like a separate. The, this is the reason that the free variables in here work. That's the way that it says. It doesn't says they are not free.
Well, they are free if you look at the statement in isolation, but they are bound if you look at the procedure around it as well.
Well, yes, but um, at some point maybe I'm gonna look. I'm gonna spot it and I will pinpoint it to it. It is not one of the procedure, blah blah blah. Yeah. So in this case, the y needs to be defined before, like in here.
Yeah,
It has to be the y when the procedure is defined, like not called but defined. That's important
yeah.
distinction. Okay, so now we
And
go to
here's
dynamic scoping versus static scoping.
here's the example program that you were looking for, I guess.
Yeah. So in here, um, the closest Q definition to the when calling P is this one, but the closest Q definition to the definition of P is this one. And which one we're going to pick will determine which type of scoping we have.
Yep.
So the original Lisp was dynamically scoped. Common Lisp scheme changed that to statically scoped. Uh, man, that like I can't imagine like there would be some situations that I would be wasting my time trying to find a bug because of dynamic
Yeah, no, dynamic scoping is definitely the wrong default.
scoping.
It's useful if you can use it
Well, it's
as
saying here,
opt-in.
right? It's saying here.
Yeah, but it shouldn't be the default
No, yeah,
by
but
no
no, no, no.
means.
But this is actually kind of funny. I don't know if this happens in this version of the book because it says in mine. It says all of this shit, but then it backtracks on it. Poggers. Like actually, you could use the name scoping for this case, and then eight, and then you go read eight. You shouldn't actually. Like I lied.
I mean, if you already know ahead of time that, okay, this is actually going to another system where the base definitions for the primitives are the same, then yeah, you can use dynamic binding and that's fine. But that's like a special case, it's not the default, right?
Yeah. Man. Let's try 1.5 hours because it's already 7 minutes to go and we're still on 61. 40 more pages to go. Data flow behavior. So now we're gonna go to the data flow thing. Okay, now we go to the operational semantics, right? Now we go
Right.
to the operational semantics. So yeah, so this is essentially our tools, right? So in the case of Karuta, we also have tools, but we have many more tools than this thing because we have multiple phases and multiple different entities. We have evaluator, code generator, registry allocator, blah blah blah.
Um,
In here,
actually, this
it's
is
way simpler.
actually this is more like this is more this is closer to being the evaluator than the entirety of Karuta, to be honest, because this is like, okay, here's the operational semantics, here's how you run a program, right? That's equivalent to the evaluator, basically.
Well, to be completely and 100% fair, this is also missing some steps because, for example, where is the translation unit from the language you write to the kernel language? We're skipping all that stuff and going
Yeah, we glossed
directly
over
to
it. Yeah, we just
the
glossed over it, basically.
yeah, but essentially we have the store, we have the environment, which is essentially how we're gonna make closures later, and this is what we're gonna use for shadowing as well. And then we have the semantic statement, which is well, the couple of the statement and its related environment. And we have the execution state, which is essentially like, if you really want to force it, you can even say that, okay, this is a state monad, fuck it, I don't care. So that's how that works. They are transactional, which is cool. It's using atomic in here, and they are sequential. But we're going to increase this later, so I guess we're going to have more stacks.
We're gonna have more stacks to introduce concurrency, yes, and we're also gonna have more stores when we get to mutability.
Yeah, that makes sense. So we have the initial execution state. So this is the empty state, of course. And in each step, the first element of st is popped, and execution proceeds according to the form of the component. We finish when the stack is empty. Uh, and then there's some states for the semantic stack, which is runnable, terminated, and suspended, and they do what you might expect. Um,
Yep,
and then we talk a little bit about environments and blah blah blah. This is pretty intuitive, right? I don't think we need to go over this.
probably not.
This is
Yeah,
essentially doing
this
the bindings. Do
yeah,
bindings.
yeah, this is fairly straightforward.
Non-suspendable statements. So you have skip. Execution is complete after this pair is swapped from the semantic stack. So this is like what? This is an OOP.
It's a no-op.
Sequential composition. This is kind of weird. Like, why does it matter if you're gonna pop it anyway to do this type of stuff? Like, why do you want to
Why?
name two statements being next to each other? This is not an application. This is just like push one, push the other.
Well, this is composition, right? It's a form of composition.
I don't see it like that. I just see it that I have as true. I do my stuff, and then I do S1,
Okay,
and I do my stuff.
let me tell you. Okay, let me tell you the purpose of this. The purpose of this is to let you treat a sequence of statements as if it was a single statement.
Oh, so this is how we do programs. That's why this is here.
Yeah, this is how you handle dealing with multiple statements. Like when you call a procedure, for instance, right? You have to push the body of the procedure into
Hmm.
the semantic stack, and ideally you want to do that in one step, right? You can't do it in one step if you don't have this.
That makes sense. Then we have variable declaration, which is essentially what the local is doing here, and this is the one that is actually doing the binding with the environment. We have variable to variable binding, which bind these and these in the store. Value creation, which again uses the environment. More lexical scoping.
I think is it the section where this actually walks through how it's implemented in the kernel language semantics?
I don't know.
I think it's a bit later actually.
Well, again, we have 40-ish pages to go. Uh, yeah, so if the declaration is in some statement that actually surrounds the occurrence, then we say that the declaration obeys lexical scoping. Identifier occurrences in a statement can be bound or free. An identifier occurrence is bound with respect to a statement if it is declared inside in a local statement, in the pattern of a case statement or an argument of procedure declaration. Yeah, man, this is just weird. Like, we're gonna go there, and there is a particular syntactical elements that chosen for case. They are just like
I
fucked. What
I
the fuck
think
did
I
they
know
do?
what it. I think I know what it is. You let me know. It's the double square brackets
Of
instead
course
of
it
the
is, man. Of course
bar,
it
right?
is. Like, why? Like, what are we doing? Let's use slash or whatever the fuck. What are we doing here?
Of course.
Uh, Free occurrences can only exist in an incomplete fragment, statements that cannot run. You can only run when everything is bound. Every identifier occurrence is bound. And there's a difference between bound variables and bound
Identifiers,
values,
yeah.
identifiers, right? Because they again, the variables are in the store, the identifiers are in your program.
Yeah.
Um, yeah, so we have an example that this cannot be run, and then we have if the fixing, and then we have closures. Um, uh, yeah, read this.
The if statement has three free variables. Well, yes, they are free with respect to the if statement, but not with respect to the entire procedure.
That's not written here. That like what is written is that the reason that this works is because two of them are formal parameters. Which, well, I understand what you're saying. To me, makes sense what you're saying. But I wasted a couple of minutes reading this multiple times because it was like, no, they are not free because they appear here first. It's essentially saying, oh, let me pick this block of code, this snippet, and just say that actually the A, B, and C variables inside the if block they are free. Like, doesn't that sound misleading? Like, come on.
Well, they are free only with respect to the if statement, not with respect to the entire snippet.
Yeah,
Yeah.
but when you say that they are free, and you don't go immediately saying, actually, because this if block is surrounded by everything else, they are not free. Like, it seems, sounds misleading to me. Like, I don't know what's the purpose of saying this type of stuff. If you're not gonna say exclusively to the if statement and immediately after that to the respect of the procedure, they are not. If you're not gonna do that, why include this in the first place?
Well, it's saying then that x and z are also formal parameters and y is not a parameter, right?
Yeah,
So y is
but
actually free
yeah,
with regard to the
yeah,
procedure as well.
yeah. Y needs to be bound beforehand.
Yep.
Um, and well, yeah, we're gonna see what happens. And then the dollar means I forgot. Is this because of the name?
Yeah, because they're saying this is an anonymous procedure, so it has
Anonymous
no name,
procedure.
and the name is the first symbol, so they replace it with a dollar. And this actually this is convenient for the syntactic sugar we define later. Like it makes it consistent with that, which is neat. But yeah,
Yeah, and then we're gonna have to have the Y in the contextual environment, which is gonna collect external references for us. And then we have suspendable statements, which is what we're gonna be waiting on, I guess.
yeah,
And then it goes a little bit. Well, we're gonna check this on chapter 4, but it's actually mentioning that we actually need to signal that something's ready,
yep,
which is. I thought there would be a default automatic mechanism for that type of stuff, to be honest. Because what if I don't want to do that myself? But anyway, then we have ifs, procedure application. Oh, this is classic. And we have the pattern matching. And then it comes the freaking. Well, not now.
well, I can give you a slight spoiler. The signal is actually tied to when the variable is bound, so we don't have to do it by hand.
No, but it's specifically saying that. No, no, okay. It doesn't say. We are the implementer from this perspective, so everything is on us anyway.
Yeah,
And then we're gonna go now. Yeah, now we go through execution. So step by step, very educational. I'm not gonna
yeah,
go through this. Like this is
yeah. No, this
essentially
is really
defining.
long.
Okay, this is one statement. This is another statement.
Yeah, this is really long, and we kind of already know this, right?
Oh yeah, even that knowing that Nathan didn't read, I know he knows this. So there's that. And then there's more
Here's
examples.
actually I like this because it gives you okay. Here's what this thing looks like when it's desugared, right? And
Yeah.
it's
So the max function it actually has all of these locals and stuff. It actually binds to an anonymous procedure. It actually removes the thing here and creates a separate temporary thing, and so on and so forth. and then everything can be this written like this, which is way better. And then we go through examples on how that works, which is again pretty normal, nothing crazy, I would say. Um, and then go with the example of having the y outside of the procedure's body, and
Yep.
then that will explain that the contextual environment will save our asses anyway, and stuff like that. Uh, I think there's a gotcha here. Yeah. So this is because dynamic scoping is not on.
Yeah, we don't do dynamic scoping by default. So yeah, this binding to y actually doesn't affect the lower bound procedure.
Yeah, because we care about when it was defined, and when that happened, it was a 5, not a 10.
Yep. Yep.
Dynamic binding. And I like my another criticism. This should be written in here. Like I deduce myself because I understood what dynamic scoping means, but this should be written here. Like it is ignored, and then you know why, and then subscript, and then you read the answer down here, and it is dynamic scoping. Gotcha.
Yeah, this is actually, yeah, we're doing lexical scoping, so the y next to the call actually doesn't matter.
No, no, no.
It's not
Yes, but
dynamic.
I'm criticizing that this is not written.
Yeah, that's fair. That's a fair criticism, I guess.
I know the answer is dynamic scoping because I understood what it means and I can properly apply it in here. But why there's no mention at all? Like,
Proper
and
tail
then,
calls.
of course, of course, it wouldn't be a Marin's recommendation if it didn't fucking mention the tail calls. So this is the call tail call optimization or last call optimization, which essentially will allow us to not blow the stack and have a constant time, well, constant size when we finish our program.
Yeah, then it goes a little bit into garbage collection, right? Because we're creating all of these variables when you're doing a loop, but actually they are all out of scope, so we can reclaim them. So it goes a little bit into how that's done.
Yeah, it talks about some about the reachability, the concept of reachability, which is essentially the basis and the foundation on how we're going to do garbage collection.
Yep.
Um, and then it talks about that when you have an unreachable piece of memory that is not reclaimable, we call that a memory leak. So for everybody confused, because it took me a few years to understand what this means during university, when you do Valgrind and it says shit, what it's actually saying is that there are allocations in your program that are not being reclaimed, but they are still there, wasting your space. A memory leak is a space waste. That's it. That's just a fancy name for wasting space. And why is this a problem? Isn't memory cheap? The answer is yes, memory is cheap. However, memory leaks that are not close and like intended in the sense that I know this is gonna leak, but I don't care. Doesn't matter. The problem is that they tend to grow. That's why we care about this shit. Even though memory is cheap, is because they grow and they waste even more time, more space. Sorry.
Um, as a nice example, actually, of when you actually don't care about leaking memory, um, a lot of command line utilities written in C actually don't do any freeing because you expect to call them from the shell, right? And it's like, okay, it's gonna run for a bit and then it's gonna finish. And then the operating system is actually going to reclaim the memory for you, so you don't have to do it yourself. In
Yeah.
that case, you don't care about memory leaks.
Yeah, but I find that to be a pretty powerful excuse because you can just say, okay, this is just gonna run for a bit, and it doesn't matter because the OS is gonna reclaim it anyway. And I'm like, that's lazy shit. Uh, because well, you can always say that, no? Oh, if you're gonna play the
Man,
game for only an hour, doesn't matter. When you close the game, it's gonna be reclaimed anyway.
no, no, but that possibly can be very long-lived. But if you know for sure that is, well,
Yeah, yeah.
bound with,
There's a difference between this is gonna run a loop, which it may end quickly, it may end in 2 days, You don't know, right? That's different from, okay, this is gonna run, and I know it's going to finish like in less than a second, I guess, or something. It kind of depends on what you're doing, right? If it's just a simple, okay, take some text, does some manipulation, outputs the text to standard out, you probably don't really care about memory leaks, but then you're also probably not using too much memory to begin with, so I don't know.
Low-level languages like
Also,
C, C,
Lemos,
go Nautilus.
you gotta go fast, man. No time for managing, well, a bunch of massive pieces of memory.
You gotta go fast. Low-level languages like C, C++, Jai, Zig, probably Odin as well. Why not? I don't know Odin, but it's probably in the same bucket there.
I think Odin does manual memory management, yes.
Often leaves reclaiming to the programmer, so that's why it's your fault because it couldn't be anybody else's in those languages.
Also, Forth, don't forget Forth.
Yeah, of course. And anyway, so again, we all know this, and then there's strategies to do this automatically. That has a hit. Well, it was especially heavy hit during the beginning of times to do automatically by the runtime.
Yeah.
But according to this book, even it's actually not as cost heavy anymore.
Well, we have experience now. We know how to do it more efficiently, and memory is also cheaper.
Yeah.
But we also have like bigger requirements, like multiplayer server with, I don't know, 1,000 players, right?
Well, that's true to some extent. We do have bigger requirements, but I don't think the extra requirements, because since the 60s, they actually are that significant in comparison to the beginning. Like, we actually need to make Pong work, man. Like, come on.
Actually, there's
Wait,
one
Pongo.
requirement. Yeah, there's one requirement actually that's kind of significant, which is having to do garbage collection concurrently. That's difficult.
Cool.
Oh, it's good we have Erlang.
Well,
Erlang
yeah.
actually Erlang has a trick. It dodges that problem entirely by saying, yeah, okay, we're not gonna share memory between processes, which means we have like each process has its own garbage collector, effectively.
Well, yeah. But that's kind of
Pretty
cheating
good.
if you think about it.
Well, it is, but
No.
it
Like,
works.
what's the
So
best way to solve the problem? To ignore it, of course. That,
no,
that,
no, not to ignore it, to dodge it entirely.
oh yeah,
But
no,
that's the
ignore it.
best way, man.
No, ignore it in the sense that people are still suffering from it, but you're just gonna say it's your problem, not my problem. Yeah, so this is essentially looking for dangling references, right? So this is the definition here.
I find it kind
Um,
of nice that it actually goes into a bit of detail about how a semi-space collector works.
yeah,
They could have
semi-space
just
collector.
said it works because we follow the references and not specify how exactly, but I think this is nice.
Yeah, it goes a little bit into the detail on how you can do like the one of the strategies to the garbage collection. It is not magic, right?
Nope.
Uh, um, um, yeah, and this is
Yeah.
essentially yeah. This was weird the first time I read it. Like, why the fuck are we doing L again? Like, what's
Well, you
what's the
shouldn't.
difference?
That's kind of the point, right?
No, yeah, but I was kind of expecting an example in which it would be imperceptible to my eye that actually there is a leak here, and if you don't notice, you should do better. You should be better. But you immediately look at it and say, "What the fuck is going on with the element?"
Um,
And then this makes it even worse. Look at this.
yeah.
Like, what are we doing? And this is just demonstrating that you can actually, like, when programming, you can actually fuck. Like, garbage collection is on a silver bullet, essentially. You still have to do your job a little bit.
Well, it does address that, right? This example is trivial, but things can be more subtle in the
Yeah,
paragraph after this.
yeah. And then we also have the problem of external resources, so, like, using stuff
Yeah.
outside of the program.
Like network connections and file system handles and stuff like that, right?
Yeah, but the try-catch thing, finalize, will solve this thing. So that's cool. And then we have the local garbage collection uses a copying dual space algorithm. What else? And then copying long, yeah, and then there's a problem of wasting time copying stuff that is actually not is going to be living there forever, right? So when you have this is the available space, this is the space that stuff is, and I need to move one from the other, you're going to waste a lot of time with data structures that may live forever because I don't know, maybe they're globals. You can use
Yeah.
a generational garbage collector to fix that.
Yep.
Closure can F your garbage collection.
I mean, if you capture a reference to something that you did not intend to capture, then yes, it can actually.
Okay, then we go to the practical language and syntactic convenience, such as being able to nest partial values. Variables can be both declared and initialized in one step. Better improvements for if and case, and then some syntax sugars for great measure. And then again, nested partial values. Um, no, this is what this is.
Yeah.
Uh, yeah, so you can literally just write this instead of this thing.
Yeah,
But
that
this
would
is
be
not a partial
painful.
value. Bad example.
I mean, it could be if you replace 25 with an actual variable,
Yeah,
right?
but the title is this, and this is the example given. What are we? Again, smaller details like this. I'm being nitpick, I know, but come on.
That's fair.
Implicit variable initialization. Yeah, so this is just be able to declare and initialize this thing. Yeah, so there is something in here that I wanted to talk about. I just don't remember where it is. There is some left or right thing that I got confused. And maybe I solved it myself. I don't remember anymore. An expression is syntax true for a sequence of operations that returns a value. Because differently than what you would normally do in a naive interpreter if you're doing yourself, we don't work on n-level expressions. Expressions are actually syntax sugar. Go figure.
Amazing. I mean, this is kind of true if you work with Prolog dialects, if you want to have like data expressions, right?
Data expressions. Well, I
Like when you have an argument to a predicate and that argument is a literal value or a functor or whatever, right? That essentially compiles down to a sequence of initialization statements, right? Whether binding to the structure or just constructing the
well, that
thing.
is true. That is true. Uh, yeah. So this is essential. Expressions that as Marinho described. But this is actually cool. So you can actually instead of saying this, you can translate this into this, and the final result is going to be x.
Flashbacks to Karuta, of course.
Yeah. Nested if and case statements. Yeah. So then we go to the horrendous syntax choice for cases. So not only they chose this, they also chose this for the
I
alternatives,
mean,
of course.
I mean, technically the hash is not for case specifically. That's just how you do a tuple with hash as the label, right?
No, this is for patterns.
No, this is a tuple.
But it's a tuple pattern. Where is the grammar?
Well, it's
Uh,
literally it's cons being up basically. It's in the
no, no, no. We have an expression there. Where is the expression grammar? Here. Um,
eval being up. Well,
yeah, no, but it's a tuple thing. I agree with you that it actually took me a while to know. Okay, what is the difference between pipe and hashtag? Oh,
type is
one is
for
for
list.
lists, another one is for tuples. Why don't you tell me those things? What are we doing? And then I only figured that out when I was like trying to match this non-synthet, non-sugary version. I was like, what the fuck is going on here? And
Oh,
I
that's
okay,
because in this case, because the tuple is actually constructed in. Uh, well, no, it actually explains here, right? The hash could have been written with the usual syntax as hash, we in quotes, right? Because you can have special characters in labels.
no, 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 but this happens after you have spent minutes reading this.
That's fair. Yeah, it would probably be better to like do. Oh, hey, by the way, this is a tuple.
Yeah. And then we have and then and or else for well some nice
Conditionals.
yeah some nice nicer sugars for ifs and conditionals. And then we have
Nesting
the nesting
markers.
markers. Yeah.
Yeah, those are actually kind of fun.
Yeah, this is very confusing to me because the final thing is this, right?
Hmm.
But the X is like, okay, I'm just like, there's a lot going on in here.
There is.
Yeah, but this also reminded me of, was it Elixir that it has the pipes with numbers? Maybe I don't remember.
I
Pipes with numbers, Elixir. Yeah, is that? Am I tripping? Maybe I'm tripping. Possible. Man, there was a language that allows you to say where is the argument going anyway. Nathan, help me please, man.
Yeah, but that's not quite what this is, right? I mean, it's kind of similar if you can
Maybe it's
find it.
Elixir. I also think that the C++ 23 is also adding that shit.
I mean, it's C++. What did you expect?
C++21 or 23 took them a while.
By the way, Marinho, why
Yeah,
does
this thing.
enclosure has that?
This thing. Yeah, that's what I'm talking about.
Why
Something
doesn't
like that.
closure have what?
A macro for like using numbers to rearrange the where the thing is piped in.
Because
It
you can use the thread first or thread last and
you
use
can also
the lambda macro to put the thing there. That's
yeah
right.
you can also just use the as thread first and as thread last, which lets you bind an identifier, which is like well, it's kind of silly, but okay.
Yeah. No, but I think this is way more convenient. Having the numbers is like, man, that's nice. Anyway, functions, which is essentially procedures in disguise. Anyway, so this is how a function is going to be written, and this is how a procedure, the equivalent procedure, is going to be. How we do function calls. Function calls with data structures. Yeah, this is actually pretty interesting. And another criticism. So
Hmm.
this f is not the same as this one.
This
This
f
f
is
is a function, and this f is the procedural version of this f. Why they don't tell me these things?
this f is a function, but like well, f
Come on.
of x. Yeah, no, that is true. This is the bottom case is just okay. This is fully desugared. Like they could have just done the desugaring for the binding, and that would probably be a bit clearer, I
They could have
suppose.
said that f here is the procedure because I see f here and this takes one argument, and I see f here and this takes two, and I keep wasting my time trying to figure the shit out. What the fuck is going on?
Well, but this f is in an expression, right? So it must return a value, which means it must have an argument for the output.
No, but this is a function, right? This
But
is what's
functions are procedures. They just have an extra argument, which is the output.
exactly. Why don't you say that in here? Because I keep
Because
saying, okay, this is a function, but this is the procedural version of the function. Ah, like they did so nice in here. Like, okay, this is that. And I kept asking myself, why not in here? And then after
by
I
the way,
figured that out, okay, go on.
okay, that's a fair criticism. But can we just appreciate that this actually does proper tail calls modulo cons, which is not something that most languages can do?
Modulo cons, I don't remember what that is.
Because this map is actually constructing the tail of the list, but it's also a tail call, you see?
Yeah, I see.
Like if you did this in most functional languages, the cons would be the tail call, but in this case, the map is the tail call because you can get away with it since you're just binding
Wait, in
variables.
most functional languages, the cons would be the tail call.
Yeah,
Do you mean like you apply F to the head, cons, tail call?
no. The cons itself would be the tail call in most languages. The construction of the list cell, I
But
guess.
isn't that what is going on here? What am I missing
Mm,
here?
no, no, it gets desugared into the example above where map is actually in tail position.
Above. You, this is not what you're talking about, right?
No, no, the full map function is defined as follows, right?
Yeah,
And then the example above with the local y, blah, 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 where you complained about the f being a procedure instead of a function, right?
yeah.
That's the line after you do the pattern match for the return value of the map function.
You need to point that line. You're talking about this?
No, the entire local block there, if you
Yeah.
replace y's with the return value, would be the then in the map function after you do the destructuring on the list case.
Uh, the then well, you said the then case, right?
In the case where you're destructuring a pair instead of new, the then
Yes.
you have f of x, cons,
Yes.
map, whatever, right?
Yes. Yes. Yes.
That's the right hand side of the binding above. Y is equals blah blah blah, right? That means this sugars into the local block, which means the map is in tail position.
Yeah, I'm having a hard time understanding that. When I write this function in Haskell, I also do this, but instead of a pipe, there's a column here.
Well, yes, but the point is that in Haskell, the function in tail position is the colon, not the map.
I'm having a hard time understanding what you're saying. The pipe here is the column, right?
Yes,
So I'm
and
doing
that's what's
cons map again.
no no no. Yeah, but in Haskell, the cons is the tail call. But in here, the map is actually the tail call because you do the cons first and then you bind the right hand side by passing the same variable to map as the output variable.
Yeah, I'm not following at all. The cons being the tail call, it doesn't make sense to me. I'm doing a cons and then doing a map again. I'm doing a
No, no,
cons
the
and doing a
cons
map
is
again.
that. No, no, that's not how you desugar that.
I don't. Yeah, I am completely confused. I'm not following at all.
Okay, what's in the tail position in the local block? Because that's what this cons desugars to, right?
You mean this?
Yes, what's in tail position in that block?
This? No?
Yes. And this is what the expression below translates to.
You're saying
See, the
that
map,
this turns into this.
oh, the then, where you do the cons, f of x, blah, blah, turns
This
into this local.
turns into
Yeah,
this.
yeah,
Ah, okay. So you're saying that in the translated version of this, the map is on the tail call position.
yeah.
Okay, I see. Sorry, it took me a while.
No, that's fair. It actually took me a little bit to understand it the first time I saw, okay, how would you actually do that? And then I saw, oh, data flow variables, of course.
Of
They let you
course.
put things in tail position that would be impossible in other languages.
Yeah, this is also the map procedure of this. So this is
Yeah.
actually something else. Okay. Okay, then we have an example. Yeah, this is the procedural version of the map.
And map is in tail position, which is amazing.
And map is in tail position. That's true. That's very true. Um, then we have more example. Okay, this is about the declare, but declare is only for interactive, right? This is only for the REPL, so who cares?
Yeah, yeah, yeah.
Who cares? Who cares? More who cares? Then we
The
have the
browser,
graphical interface, so small talk, and then
small
we
talk
have
style, yeah.
data flow execution, which is going to be doing the blocking, and then we finally go to exceptions, which is going to have a try, a catch, and a finish or finalize. I keep forgetting.
It's finally, I think.
Yeah, and then this is a very good image because it talks about where, okay, we're going to go to, when we have a problem, we're going to go to a boundary, and the boundary's purpose is to handle problems. That makes
Yep.
sense. And then you're going to have a try, a raise, and a catch, and a finalize.
Not
Uh,
finalized. Finally, those are two different
Finally,
things.
sorry, I keep again. Um, Finally. Um, and then it talks about, okay, but you need to tell which problem it is because then you need to take care of things properly.
Yeah,
And then
yeah.
you
I
go to
think this point.
like
Yeah, the point that it
random
makes there is,
interpreter here,
of course, of course,
like out of nowhere. Like there it is.
of course.
And then we have, yeah, so trying to do some operations. We have the catch. You were about to say something.
Yeah, I was just gonna say, it actually raises a good point because we have data flow variables. We can actually throw an unbound variable and say, okay, we know there's a problem. Let me figure out what the problem is, and I'll tell you later. Basically.
Yeah, which is weird, right? Like you tell me there is a problem, you don't tell me what is the problem, and then go figure. Uh, yeah, that's written somewhere in here. I don't remember where, but that's written actually in here.
It's in that. It's right there, actually. The first paragraph in this page.
Because an exception can be an amount variable, raising an exception determining what the exception is can be done concurrently. That is a way to make exceptions even more cursed. Uh,
I mean, it fits with the language model, right?
and then you go through the operational semantics of having these things. Nothing out of the ordinary. And then we have the finally, which is going to use to close the file descriptors, for example. So yeah, this is where we're closing the file. We also have then pattern matching for the try catch, so it's even more convenient to use. And then we have some system exceptions. This is actually kinds of exceptions, like types of exception. So you can say stuff like
Yeah,
that. And then we have some advanced topics in here, which I don't remember exactly. It talks a little about lambda calculus.
it does.
A possible to calculate is pure functional language. Let's examine how the declarative model relates to pure functional programming. So yeah, this is the Oz version. This is the lambda calculus. Well, you have to figure what the fuck these other things mean, but
Well,
um,
it does give the definitions there, right? But yeah, you do. You need to figure them out.
actually, it gives
Yeah,
the
the definition
semantics
of
in Oz of them.
yes in Oz, not in the lambda calculus.
The declarative model is more general in the lambda calculus in two ways. First, it defines functions on partial values with unbound variables. Second, it uses a procedural syntax. It can define a pure functional language by putting two syntactic restrictions. Always bind a variable to a value immediately when it's declared. That makes sense. Use only the function syntax, not the procedural one. And there we go. Pure functional programming, folks.
There's one small caveat. You also need to change the translation of. You need to change the translation of for function calls, blah blah blah. Yeah, it's the second point there. For function call inside of data structures, do the nested call before creating the data structure, which means map cannot be in tail position anymore. And this is to avoid putting unbound variables in data structures.
And then we have flavors of functional programming. So we have dynamic typed scheme, and we have statically typed functional languages, Haskell and SML. Um, and then we don't have data flow variables in those languages. Well, is STM declarative concurrency?
Is STM declarative concurrency?
I don't know what declarative means. So
No, because well, the implementation is declarative, of course, because it's monadic, but it doesn't actually implement this declarative model because the STM variables are not single assignment.
okay. In declarative model, functions are eager by default. Strict evaluation, classic thing.
Nathan
Uh,
asks, do we have a formal computation model for data flow programming? We do. I think it's chapter 4, right? Where it gets to declarative concurrency and we define the model and then we look at the techniques the same way we're doing here. Except the model is going to be much briefer to define because you can just reuse most of this.
there's the observation in
I
Haskell.
mean,
Go, Nathan.
well known like the actor model.
Well, there's the pi calculus. and a bunch of other process calculus that you can process calculi, I should say, because plural.
That
Um,
you can kind of get a subset to make this, or
Actually, let me be a bit more precise. The pi calculus is not really for declarative data flow because um, it's for some modeling something more like Erlang, I suppose, based on the actor model.
mm,
Okay. And then there's an observation here that instead of saying that Haskell is a lazy functional language, is a non-strict language. It's identical to
Yep.
laziness for most precise purposes, but we're gonna see the difference later. I'm very excited to see the differences. And then we have unification and entailment. So unification, I believe when I read this is Prolog's unification, right?
Yeah, basically saying, okay, I have these two data structures. They may have three variables. Are they equal? And if not, can I bind variables to make them equal? That's is unification in a nutshell.
Yeah, but this unification then doesn't actually imply that they actually are like bound to and literal, right? They can
It
actually be
makes
unified, both being unbound.
yes, they can.
Yeah, that's very weird.
Yeah, if you have two unbound values, unbound variables, and you try to unify them, it's just going to say, okay, for now on these variables are equal. If I bind one of them, I automatically also bind the other.
Yeah. So testing when a variable is equal to a value is a special case of entailment. So that's interesting. And we have unification,
We
which
just saw
well,
that in Karuta, right?
yeah, we definitely are very accustomed to that. But this also explains the pattern matching in a way, because it doesn't explain it like that. But you can use this unification to do the pattern matching, right?
Yep.
Some sort of some flavor of pattern matching.
Well, unification on its own is basically just destructuring. You need the conditional around it to do pattern matching properly, which is what you do with case essentially.
Yeah, no, but but this allows us to destructure things and just
Yep.
like
Yep.
say that this is that, this is that. So yeah, yeah, unification of size cyclic structures. Yeah, this is pretty funny. So if you
Yeah.
unify those things, the end result is this.
Yeah, and you need to be able to do cycle detection to do this properly as well.
Yeah, exactly. And then it even talks about that. So we have logic variables is a basic operation of logic programming, as we saw and we implemented ourselves. Which is not that hard to be honest. Like it's actually fine. Like it doesn't take like maybe the backtracking thing takes cleverness. Not maybe, definitely
Yeah,
takes cleverness, but the unification by itself is like, okay.
yeah, yeah. Backtracking is easy to implement if you just want to make it work, but it's hard to make it efficient, you know. And that's why you have the whole Warren's abstract machine.
Yeah. Yeah, it talks more about the unification algorithm, primitive bind operation, and then the algorithm,
Handling
which is
cycles.
I think that we did this in a way, if you think about it.
Yeah, we kind of did.
And then we need to handle cycles, as you mentioned before. How to display cycle structures, and then this is right. They essentially cheat, right? This is cheating.
I mean, you have to, otherwise you end up with an infinitely sized textual representation, which you can never finish printing, right?
Yeah, so this is like okay, R14 is a textual representation, but if you want different sorts of representation for display, then we do something about it. Um, entailment and
Entailment and disentailment, those are
entailment
basically
checks.
equality and inequality checks.
Yeah, but it talks about
Like,
structure equality.
yes,
Um, all pairwise corresponding nodes have identical values or are the same node. We call this structure equality. So very cool, very familiar as well. Like structural versus nominal equality, we know what that is about. And then yeah, it has more to say about dynamic and static typing. So the first thing that it does, which is pretty awesome in our opinion, it distincts being strongly typed from being weakly typed. And then we go to dynamic and static because some people confuse those things.
yeah, they're separate.
Yeah. So it's pretty much a consensus that everything should be strongly typed. Whether we're going to discover that at runtime or not is the big question. And then that's where dynamic and static types
what do you
terminology comes in.
mean? People use JavaScript all the time. and it just coerces shit.
Well,
Oh
but
I don't
no,
even
JavaScript,
but
agree
everybody
what's
agrees that's
strongly
shit,
typed.
right?
yeah,
Everybody agrees.
I don't
yeah.
know,
The
man.
problem, yeah, the problem with JavaScript is not really that it's dynamically typed, although some people don't like that. The problem is that okay, there's all these implicit coercions everywhere that make it hard to
Oh
figure
yeah.
out what's actually going on.
Yeah, not only it's dynamic, it is weakly typed.
Yeah,
Like, um, okay, so let's actually go to the motivation. The basic principle is static type puts restrictions on programs someone can write, reducing expressions of the language in return for giving advantage, such as improving your messages, catching ability, efficiency, security, and partial program verification. And then he essentially explains that, okay, there are actually pros and cons for both sides. Dynamic typing puts some restrictions on programs one can write, but this is also kind of like a hot take because do we want that? To be precise, all synthetically legal programs can be run. Some of these programs will raise exceptions, possibly due to type errors, which can be caught by an exception handler. Dynamic typing gives the widest possible variety of program techniques. The increased flexibility is felt quite strongly in practice. The programmer spends much less time adjusting the program to fit the type system. Yeah, all of this is true and desirable, but this one is kind of a controversial. Dynamic typing makes it a trivial matter to do separate compilation. Modules can be compiled without knowing anything about each other. That's also true. This allows truly open programming in which independently written modules can come together at runtime and interact with each other. It also makes program development scalable. Extremely large programs can be divided into modules that can be compiled individually without recompiling older modules. This is hard to
yeah,
do with
and
static typing because the type discipline must be enforced across module boundaries.
which is
Oh,
why OCaml and ML, the dialects that did not go the Haskell way, they have that very nice module system, right? The whole point of that is to say, okay, we want modules, but we also want static typing across modules. So how do we do it? And
yeah,
that's a
and I
solution
would
to
I
this.
would argue that this is not always true because you actually can at the boundary, like at the frontier of each module. Oh, well, compilation unit. Maybe you can do some sort of cheating, right? So in Haskell, the first thing that comes to my mind is coercion and then typable. You can just say, okay, fuck it. I don't know what's coming, and it's typable. Who cares?
Actually, typed racket has an interesting take on this because you need to be able to interact with normal racket, which is dynamically typed, right? So you need to introduce some contracts to do the checking at the boundary as well.
Yeah. Dynamic type allows us to do scripting. No, that's no news. Everybody knows that. And then we
Wait,
go
what is the relation there?
what? What do you mean?
Scripting and dynamic typing.
Well, it's kind of self-evident, right? Because if you want to do a script, which is usually something very dirty and very fast, that you're just experimenting between an idea and its implementation, being dynamically typed makes it you finish the scripting phase faster. That's why Python is that. That's why Bash works like that. That's like there's a lot of reasons that these languages that are they were made to be scripting. Then people said, okay, actually, I don't want. I think having types is a problem. I actually want to do this all day, all night, and I want to be paid for it. So let's put more infrastructure into it. So let's put Node.js, let's put Django, let's put all those things there because then I can live with the feeling of doing scripting all the time, but actually now I'm treating it as a system language.
People are weird. I still prefer Dev Sharp scripts.
You are rare, my friend. You're very rare. Like even Zosing himself, which 100% I know hates Python, he opens Python constantly to do some sort of scripting shit. Like I want to know what is the result of this very cursed mathematical operation. He just like Ctrl Shift T, new tab, Python 3, and then just do it in there.
I would reach for Guile first because, well, I'm running Geeks, so I just have Guile. It's a fact of life.
Yeah.
But yeah, I can see why people would use Python for this. And to those people, I say, dudes, just use Lua. What are you doing?
Well, I don't know. I haven't done much scripting in a while, to be honest. Even knowing that I can just use like scripting capabilities of Haskell anytime, even knowing that I do it rarely. I don't know why exactly. Maybe because in Clojure I just opened the REPL. I don't know. Static type allows
Well,
to catch more errors at compile time. Go on, Marie.
no, I was just gonna say we should move on.
The compiler's type checker verifies the program satisfies this partial specification of the program's behavior. This is very powerful. Static types allows more efficient implementation because the compiler knows more stuff, so it can do more under the hood magic tricks,
Yep.
such as the classic Boolean example. And then there's also security improvements. And then it goes, okay, usually it's just war. Usually the choice between these two is just war. It's blood on the table. Adherents of dynamic type relish the expressive freedom and rapid turnaround, and gives them and criticize the reduced expressions of static typing. Remember, Nathan, what you told me? You told me something about this the other day, huh?
No idea.
Okay. Yeah, your memory is getting worse, man. Where is the comment?
Dude is literally
What?
getting the message.
Oh, of course I am.
uh,
Repeat after me. Constraints are power. Quote.
All
Uh,
right, he did say that, didn't he?
on the other hand, adherents of static typing emphasize the aid it gives them for writing correct and efficient programs, and point out that it finds many program errors at compile time, and it allows compiler-assisted programming. Little data, hard data exists to quantify these differences. The differences are not great. Programming static type is like word processing with a spelling checker. A good writer can get along with it without it, but it can improve the quality of the text. Yeah, this sentence has a problem, which is assuming that the writer is a good one.
Which may not be the case, to be fair.
And then what are the chances that's the case? That's actually the big question.
Well, that depends on your sample, right?
Historically, and you can use any sample size.
Well, the larger it is, the less likely this is to be true, unfortunately.
Static type is recommended when the programming techniques are well understood and when efficiency corrections are paramount. Dynamic type is recommended for rapid development and programs must be as flexible as possible. Just application prototypes, operating systems, and artificial intelligence applications. Yeah, like I can deny this. Dynamic typing when you just want to see a concept working. Like man, I really just want to see this graph in 3D. Like that's it.
I just want to put
That,
this picture on the screen, you know?
yeah, that is just one tiny, teeny detail there. If that's on your work, it's usually not just a prototype that you scrap. It
Uh,
will
that's not
be
true.
there for
I
years, maybe.
during work, not my current one, but previous work, I actually was asked to. Okay, actually we don't know if this is gonna be worth it. So try discover if it is. Like, what are
Well,
you gonna do there?
they know something. They know something. That's not usually how people do it.
They know something. They know. Uh, a bit of order can be added, gaining some of its advantages. For example, different kinds of polymorphism add flexibility to statically typed function object-oriented languages. It is an active research area to design static type systems that capture as much as possible of the flexibility of dynamic type systems. Oz is dynamically typed.
But there's also Alice, which you probably didn't know about.
Well, I knew because I read.
But before reading this, right?
I didn't know Oz in the first place. Imagine its sibling. And then yeah, Alice apparently is an statically typed language that has much of the expression of Oz. And it's interoperable, which is cool. Whew, 1 hour and 50 minutes. Ah,
Yeah, this was a bit longer than expected, but
yeah,
well,
yeah.
what can you
It's
do?
it's 70 pages, man. What were we thinking? What the fuck?
Yeah, it's just a lot. Um,
Okay, let's now determine what's gonna be the next thing.
We definitely should not do the entire next chapter at once because, like, for sure it's too much.
Let's define how much is gonna be that then.
There's an
Oh,
entire subchapter on what is
oh, it's
declarativeness.
100 pages.
Yeah, it's a lot.
It's
It's actually a
120
lot.
pages. Damn. One moment, please, guys. Oh man, it didn't click. I paused the recording when I left. Okay, so long story short, we decided to go with from 3 to 3.4. That's what we decided to
Yeah.
do for next time. So see you next time. I'm gonna finish the recording.
See ya.